Hey folks, it's Dr. Gilchrist for this week's lecture. We are going to be talking about bivariate correlational research. So this covers Chapter 8 in your textbook. Chapter 9 covers multivariate correlations. I will not be teaching on that. If you are curious and you want to learn more, feel free to read the chapter at your own leisure. But after this week, we are going to jump right into talking about experiments. I do have a couple of quick reminders for you. So your 50-point introduction, the second draft, is due next Thursday, April 2nd at 11:59 p.m. Central Standard Time. I'd like you to send me a copy that has been peer reviewed by two people. So that can either be in an email with a Word document, or that can be through a Google Doc. I would also prefer you to, in addition to that copy that has two sets of eyes on it, please provide me with a copy to give you feedback on, because I am going to be grading these and giving you feedback for the final draft at the end of the semester. Homework 7 is due April 2nd. I have already pulled up the handouts that you need and an article to read if you are inclined on looking at correlations between introversion and extroversion and what type of landscapes people tend to prefer. Quiz 7 will post April 3rd. It is due April 10th, the following Friday at 11:59 p.m. Central Standard Time. So here's what we're going to talk about today. We're going to talk about what bivariate correlations are, and we're going to talk about how to consider association claims, including things like the bidirectionality problem, the third variable problem, and also we're going to talk about moderating variables, things that can affect what kind of correlation we get. So what are bivariate correlations? So most correlations that we are going to talk about in this class, so if you hear me talk about a correlation coefficient, or if you hear me use a word like Pearson's R, generally in this class, if we talk about a correlation, it is technically a bivariate correlation. A bivariate correlation is an association that involves two different variables. So what you're looking at here is sample data from Mel and colleagues in 2010, looking at a score of personal well-being, and then with these little listening devices that they called EARs, we are looking at the percentage of a conversation scored and rated by raters that would be considered a deep conversation. So the reason that we can look at a bivariate correlation with this is because we are looking at two different variables. We're looking at a subjective score of well-being, and we have a percentage of conversations that were rated as being deep. So we have these two different variables. Now, I want to be really clear. There are a lot of studies that may be looking at multiple variables, but anytime that we are looking at a correlation, we're only going to be looking at two variables at a time. So a correlational study can look at a lot of different variables, but each correlation is only going to look at two variables. So here is a study by Cacioppo and colleagues in 2013 looking at marital satisfaction. So this is a categorical variable. Where did you meet your spouse, either online or off, and a marital rating or satisfaction rating. Here we're looking at the Sombomatsu study looking at multitasking frequency, and then they were also looking at a test of working memory capacity known as the operation span task. If you've had me in cognitive psychology, you might remember that operation span is basically when I give you a bunch of sequences of mathematical equations to solve and a word that you also have to remember at a later time. So you're processing a math equation and you're trying to store information as well. And we use that as a measure of working memory ability. So both of these cases are cases where we are looking at a correlation between two different variables. So how do we describe the association between two variables? And we've already talked about this a little bit. We've talked about the fact that correlations can be either positive, which means as X increases, Y also increases. We've talked about whether or not correlations can be negative. So as X increases, Y decreases, or a zero correlation. Absolutely no relationship between the two variables at all. So what you're looking at here is a plot of data, fabricated data from the MEL study. So on our y-axis, we have the percentage of deep talk, and here we have a z-score, so a standardized score of well-being. So higher scores mean greater well-being, lower scores mean less well-being. So my question is, we've got a scatter plot of all of these different scores, and we have a line of best fit. So if you look at this data, my question to you is the correlation positive, is it negative, or is it zero? Now in this case, hopefully you said that it was positive. So notice that as the percentage of deep talk increases, the well-being increases. So this is a positive correlation. Now you'll notice though that there's still a lot of scatter. So a lot of people who have really high well-being scores, they're pretty variable in terms of their percentage of deep talk. So this is a positive correlation, but you'll notice that the line is not super angled. It's actually pretty close to being flat. So if we had to rate how strong the correlation is, we would say, well, it's not bad, but it's not great. But we have some very special guidelines that can help us determine whether the correlation is weak, medium, or strong. So we have some guidelines by Cohen for correlation coefficients, and this is based off of work he did in 1992. So this is based on R, or Pearson's R, the correlation coefficient. So when we talk about strength, we're only interested in the actual numerical value. We're not really interested in whether the correlation coefficient is positive or negative. We're more interested in the magnitude of that correlation coefficient. So according to Cohen's guidelines, an R of approximately 10.1 or negative 0.1 would be small or weak. So it's a pretty small effect. If they have a correlation coefficient of 0.3 or negative 0.3, that would be considered a medium or a moderate correlation. And if we have a correlation coefficient of 0.5 or negative 0.5, that would actually be considered a large or a strong correlation. And I know that that's kind of surprising that 0.3 on a scale of 0 to 1 would be considered medium and 0.5 would be strong. But remember, we're looking at human behavior. We're measuring aspects related to people, and people are pretty variable. So the correlation that we obtained here, so our Pearson's R is about 0.28. According to Cohen's guidelines, we are kind of rounding up a little bit. This would be a medium effect size. So what about this correlation? So this is the study looking at multitasking ability and the frequency of medium multitasking. So higher numbers here mean that people are multitasking more. Here, lower numbers mean they're multitasking less. Higher O-span scores mean a higher working memory capacity, better capability of trading off storage and processing. Lower numbers mean a lower working memory capacity. So my question to you is the correlation positive, negative, or zero? Additionally, is this correlation strong, moderate, or weak? So first of all, if we want to answer this question, let's pay attention to kind of where all of the dots tend to be scattered. And you'll kind of notice that there's this very gentle, it's hard to discern, but we do see that as O-span scores increase, the frequency of multitasking decreases. Likewise, the lower that our O-span score is, the more likely we are to see people engaging in medium multitasking. So odds are pretty good that this is a negative correlation. Now the next question, Is it strong? Is it moderate? Or is it weak? And you can kind of see here, it kind of looks like a blast of gunshot. It's very, very scattered. And it's very, very difficult to make out where a line of best fit would be. And if you're having trouble figuring out a line of best fit here, odds are pretty good. It's a pretty weak correlation. It turns out, based on this data, the correlation is negative. It's R equals negative 0.19, and just given this very, very low magnitude and given the great deal of the scatter, it's very easy to see that this correlation is quite weak. Now, there are different ways that we can describe these associations. So these scatter plots work really, really well when you have data that is not categorical. So when you have like quantitative data, especially if it's continuous and you have two of these variables, scatter plots are pretty good at this. But there are some different ways that we can describe and graphically show these associations, and part of it does depend on how many variables are categorical. If you don't have any categorical variables, use a scatter plot. It's going to make your life a lot easier. It'll help you recognize and identify the direction that your correlations are in, as well as their strength. But what about if one of our variables is categorical, or if two of them are? Now, one thing I will mention very, very quickly, a study is only going to be considered correlational if both variables are being measured. If you are manipulating one of those variables, this is not a correlational study. Instead, you have an experiment, or potentially a quasi-experiment. Now, if we're describing data with categorical variables, you can actually use a scatter plot or a bar graph. So in this case, we're looking at the Cacioppo and colleagues study, looking at marital satisfaction versus whether or not they met their spouse online or offline. And so this scatter plot looks a little different from previous ones that you've seen. And it's kind of hard to determine if there's a difference between these two variables. You can clearly see that there's a lot of spread, but you'll also notice that because there is so much spread, this is probably telling me that there's very little difference between where you meet your spouse and the effect it has on marital satisfaction. This, the group that met online is overall a little bit higher, but possibly not to a level that would be what we call significantly different. Generally, though, if you have one categorical variable and the other is numerical, a bar graph is often easier. And a bar graph will be looking at group means rather than looking at the overall scatter. Now, I would say that when you look at your data, even if it is categorical, it's not the worst idea in the world to get a feel for the spread of your data. Outliers, like really extreme values, can really drag your means around. Means are very, very sensitive to outliers. And so having an image of this spread is not the worst idea in the world. But generally, if we have one categorical variable and one numerical variable, in this particular instance, it's easier to look at group means. Now, because you're comparing group means here, we can actually look and see if there is a difference between them by doing a statistical test known as a t-test, where we basically compare the group means to each other relative to the scatter that we see here. Now, just from looking at both of these graphs, it's kind of clear that there doesn't really seem to be much difference between these two groups. Now, we're talking about this in a correlational chapter, but I would actually argue here, now we aren't actually manipulating things here. We're not manipulating where people met their spouses. That's not something that you can actually manipulate. But we're looking at something and basically dividing people into groups based on a subject variable. So I would actually argue that what you're looking at here is not necessarily a correlational study. Instead, it is what I would call a quasi-experiment. We are actually looking at the effect of something that we can't actually manipulate, but we can look at different groups and divide people into different groups based on these pre-existing variables. So I would say that this is not correlational, rather it's quasi-experimental because we can't actually manipulate it. Now, let's think a little bit about association claims and correlations. Now, as with all claims, whether we're talking about a causal claim, an association claim, or a frequency claim, we need to think about the 4 major types of validity. And we're going to go through each of these in turn. First, we're going to talk about construct validity. So basically, we're looking for a theoretical construct that this variable is supposed to measure. So how well did we measure our variables? We have statistical conclusion validity. How well do our data actually support the conclusion that we have? We'll also talk about internal validity. Can a causal inference be made? Here's a hint with correlational data. No, you can't. And we'll talk about why. And then finally, we have external validity. Does the association actually generalize? Now, you'll notice that I bolded the first 2. It turns out for association claims that we're making through correlations, these 2 aspects are probably going to be the most important ones for us to consider. So let's start by considering construct validity. And these are really important questions to ask. So how well were my variables measured? Is the measure reliable, and is it measuring what it says it will? And this is one of the things that the MEL study of deep talks and well-being did very, very well. They operationalized well-being in terms of performance on a test. For looking at how much of conversation was deep, they had those listening devices that they called the EARs, the recorded conversations, and then these were scored by raters who had been well trained with very strong inter-rater reliability. So when we're talking about representing a concept in our correlational studies, we need to make sure that we have operationalized our variables, that they are reliable, and that way we are ensuring our construct validity. This is also a good opportunity to think about aspects that we talked about before, like having good face validity, having good content validity, making sure we're covering all possibilities for that content, and having converging validity with similar measures and divergent validity with different measures. But now let's talk about statistical conclusion validity. And we're going to go into each of these in bigger detail. Important questions that you need to ask when you are developing a correlation coefficient. First of all, what is the effect size? Second, is our correlation statistically significant? And then other things that are specific to thinking about with correlations. Are there outliers? Is there a restriction of range? And is the data linear or is it not? So let's start by talking about effect size. So generally, effect size is kind of a vague measure when we talk about effect sizes, and that's something that you'll learn more about in the fall, that the way that we talk about effect size can be really, really vague. Now, when we talk about effect size in the context of correlation coefficients, generally what I mean is that larger effect sizes, those happen because of stronger correlations. And stronger correlations will often give more accurate predictions, and they're less likely to be erroneous. So your book gives a really good example. So here what you're looking at is a child's height at age 2, Hugo's height at age 2. And so we can make predictions based on correlations, based on Hugo's height as a 2-year-old, what his height will be as an adult at age 18. So if we know his height at age 2, we can make a pretty good prediction of what his height will be at age 18, because there's a very strong correlation between your height at age 2 and your height at age 18. And you can kind of see how very tightly packed these scatter plots are. This is a pretty strong correlation. Now compare that to a weaker correlation, mother's height and son's adult height. So here's Hugo's mother's height, Here's the prediction for Hugo as an adult. And then notice that this data is far more scattered. They're less tightly clustered around the prediction line. This is a weaker correlation, and as such, the prediction will probably be less accurate. It's prone to more error, and we also have a smaller effect size. Now, here's what's kind of interesting. Generally, larger effect sizes will give us more accurate predictions. And when everything else is equal, a larger effect size is going to typically be considered more important than a small one. However, there are some exceptions. One that gets discussed quite a bit is the role that taking an aspirin a day can play in reducing heart attack risk. Now, I will kind of tell you that this correlation is fairly small. It's pretty weak. It is a very small effect. But if we're talking about something that could potentially reduce your risk of death due to heart attack, this is a case where this can be an important effect, even though it's small, because we're talking about something that's life or death. Now, thankfully, most of the correlational data that we're looking at are not life or death matters. And so because of that, it's generally better to focus on those larger correlations and those larger effect sizes.